Okay, and so the final thing we're going to be looking at in our applications of differentiation topic is maximum and minimum applications. And this is really just an application of finding stationary points. This is probably the meatiest part of this topic, for want of a better word, and probably, the part that leads into the most genuine kind of application problems. And these, as I said, the maths is really just about the maths of finding stationary points, but the challenge here is in the formulation of the problem and the creation of the equations. So you would have done problems like these back when we looked at cubic applications and things like that previously. So hopefully some of these processes and techniques are starting to become a bit familiar, but it's really important that we continue to work on being able to deal with and formulate worded problems into mathematical problems. Okay, so let's just have a think about this particular sort of application. So if we were wanting to maximize or minimize a particular quantity, what we need to think about that as we need to find the highest or lowest point of the graph of that quantity. And this requires us to be able to consider stationary points. So for example, the graph pictured shows the profit per week of a cinema compared with the amount charged per ticket. So we've got amount charged on the x-axis and profit made by the cinema on the y-axis. And we're seeing that this follows a sort of parabolic relationship or a quadratic relationship. So what we're seeing is there's a tipping point that we're interested in finding. Okay, if we charge too little for the tickets, if we charge really small ticket price, we're just not making enough money off each ticket, and so we make low profit. The more we increase our ticket price, the more profit we make. The more we're charging the customer, the more profit we make. Okay, there's going to be a sweet spot where we can work out what is the ultimate ticket price for our maximum profit. Okay. But what we see is if we were to start to charge more than that, the profits actually start to go down. And that's because we're actually overcharging for our product, and fewer people, the price boots to the point where it's just a bit too prohibitively expensive and fewer people start to come. Okay, so we want to think about that maximum profit point, that nice sort of sweet spot, and we can see that from this graph here. Okay, so what is the maximum profit that the cinema can make in a week, and for what ticket price does this occur? Okay, so the maximum profit is the y coordinate. The y-axis is about profit. Okay, so the maximum profit is going to be $3,062.50. Okay, and that is when we sell tickets for the price of, now that's what the x-coordinate of this point's about, the ticket price would be $17.50 to maximise that profit. So charging less than $17.50, people are still coming to the cinema, but we're not making as much profit as we could be. Charging more than $17.50, the cost has become high enough that some people start not to come. So we're selling less tickets even though we're selling for a higher price, and so therefore the profit is down. Okay, so to solve problems of this nature, these are the processes, the steps that I want you to think through in terms of formulating and solving the problem. So the first thing is to identify from the question, what is the quantity that I'm trying to minimize or maximize? So in the above example, we were trying to maximize profit. Okay. We might be trying to minimize cost in a different example. We might be trying to maximize area or minimize area. We might be trying to maximize or minimize time. So what is the quantity in the question that we are trying to maximize or minimize? That's the first step. The next step is the hardest one. Okay, and the next step is to construct from the information in the question a function to describe this quantity. So a function to describe the cost if we're trying to minimize cost. A function to describe the time if we're trying to maximize the time. A function to describe the area if we're trying to maximize the area, or whatever it might be. Okay, and that function needs to be just in terms of one other variable. Okay, so you can't have C in terms of, three other quantities, three other variables. That needs to be just in terms of one other variable. So as I said, that's the hardest part. Once we've then got our function, we need to find the minimum or maximum value of this function. And this usually requires us to think about the stationary points. We'll talk a bit more about this in the next video, some other things that could happen, but ideally, ultimately you still need to consider the stationary points in the problem. So that is to solve the derivative equal to 0 for the stationary points, and also then to justify the nature of the stationary point. So if we're trying to minimize cost, it's not enough just to say, oh, that's the value that makes the derivative 0. We need to actually know that that's actually a minimum stationary point. If it's a maximum stationary point, it's not going to be a minimum cost at that point, it'll be a maximum cost. So justifying the nature of the stationary point using a sign diagram, or you might already have a graph drawn that you could refer to. And then part 4, it seems really obvious, but I write this really frequently on tests, and that is to answer the question. So does the question ask you for the minimum cost, or does it ask you what does X have to be to give the minimum cost? So specifically about, or could ask you different things, what does it actually ask you? It might ask you for more than one quantity, so making sure you've actually answered the question. Okay, let's work through 3 examples here. A farmer plans to, or is planning to, construct a new pig pen. Let's get rid of the is. A farmer plans to construct a new pig pen. The pen is to be rectangular and is to use an existing wall for one side. Find the largest possible area for the pen, given that the farmer has the materials to build 100 metres of fencing. Okay, now this is probably the simplest kind of example we get. This is quite a common example, and actually we don't technically need any calculus to answer this question because what we get is a quadratic relationship. So we've got a fixed wall already, and we're going to be building a rectangular pen up against that wall. So we only need to actually build 3 sides of the pen with the fencing. Okay, so we've got 100 metres of fencing, so we know that that total perimeter is going to be 100. Okay, which means that if we were to think about, the dimensions of this rectangle being x and y, the perimeter tells us that our perimeter is 2x plus y, and we know that has to equal 100. Okay. Now, I've jumped around a little bit here because remember the first thing we want to actually identify in the question is what is the quantity I'm trying to maximise or minimise. So we are trying to find the largest possible area. So we're trying to maximise area. And so that means what I'm trying to do, and I should have clarified that earlier, is I'm trying to now create an equation for the area and an equation for the area that has only one unknown in it, one other unknown other than area. So I know that we're trying to maximise area. Okay, and we know that the area is equal to x times y, but that's got 2 variables in it. So that's where this bit of information comes in, because we now have a connection here between x and y, and we can rearrange to make x or y the subject here and put that back into this equation to get rid of x or y. So here it's easiest to make y the subject. So y is going to be equal to 100 minus 2x, and then we can put that into our area equation, and so we know that area is x times 100 minus 2x. Now you could write that in lots of different forms. You could take out that common factor of 2 there and write it as 2x times 50 minus x. You could expand it out and have 100x minus 2x squared. All of those are the same thing. But we want to find the maximum area. Now, as I said, we technically actually don't need calculus here, because this is a quadratic relationship. Okay, so I already know, looking at all these different forms of the graph, that this is a sad parabola with x-intercepts at 0 and 50. And if you don't know that from that equation, some work on quadratics needs to be done. Okay, so sad parabola 0 to 50. Now my axes are representing area, which is going to have to be a positive quantity, and x, which is the width of the pen, or the length of the pen, or the depth of the pen, however you want to describe that. And so both of these quantities have to be positive. So I'm not going to draw my graph past the x or y axes, I'm just going to stay up here. So we know that that is 50, 0, and we know that that is 0, 0. Therefore, because this is a quadratic, that's why we don't need calculus to find that turning point. Okay, the parabola is nice and symmetric, so the x-coordinate of that point will be 25, and we can sub 25 in to find what that means for area. So we can put, say, 25 in here, which would mean, so we can see already, and that's going to be the maximum area. So this value here will be the maximum area. Okay, so we can see here that maximum area is going to be A at 25. Sorry, I might just write here where I've got some room. Sorry. Is going to be A at 25, which I'm going to go into the, it doesn't really matter, the first or the second version, the factorised versions. So if I go into the top version, that's going to be 25 times 100 minus 2 times 25, which is 50. Okay, which is the same as having 12.5 times 100. So that means 1,250 units here. The perimeter was in meters, so everything is meters and meters squared for area. Okay. So what am I trying to maximize? Area. I've come up with an equation to describe the area, and now I've found the maximum point of that equation. I haven't needed any calculus to do that here, and that's fine. Okay, different function, we would need some calculus. So we've found and we found therefore the maximum area. We've got a graph here, so it's clear that that's definitely maximum area. My graph justifies the nature of that stationary point. All right, let's have a look at example 2. A piece of wire 40 centimeters long is to be cut into 2 pieces. One piece will be bent to form a circle, the other will be bent to form a square. Find the lengths of the 2 pieces so that the sum of the areas of the circle and the square is a minimum. Okay, so I've got a piece of wire and it is 40 centimeters long. Okay, I'm going to cut it. Doesn't say necessarily in the middle. That's what we want to work out. Where should we cut it? Okay, I'm going to cut it, I don't know, let's just say here. Doesn't really matter. So then if I say I'm going to cut it into 2 bits, which are going to be, that's going to be x centimeters, and that's going to be, sorry, not x, 40 minus x centimeters. Okay, so we've cut our piece of wire into 2 bits. We want to work out, therefore, what should those 2 lengths be, so what should x be, so that the sum of the areas of the circle and the square is a minimum. So we're going to take one of these pieces and bend it into a circle. So it's going to make my equation a bit easier if I take the simpler equation to bend into the circle, I think. Okay, and I'm going to take my other piece and bend it to form a square. And we want to think about what are we trying to maximize and minimize here. So we want to find the lengths of the 2 pieces. That's what we want to find. That's part 4. That's what to answer the question. So that the sum of the areas of the circle and the square is a minimum. Okay. So we need to come up with an equation or a function that describes the sum of the areas of the circle and the square. Okay. So we know that what we now know here is that the perimeter of this circle is equal to, or the circumference of this circle has to be equal to x centimeters, because we've bent the wire to form the circle. We know that circumference of a circle is 2 pi r, and that has to equal x, and so therefore r has to be x on 2 pi. So then once we know what the radius of the circle is, we can think about the area of the circle. So the area of the circle is 2 pi r squared. We now know that that is r, and so the area is 2 pi on x on 2 pi squared. Okay, so that is 2 pi over 1 times x squared over 2 pi squared, and so that 2 pi will cancel with one of those, and we've just got x squared on 2 pi. So I'm just seeing how much room I've left myself to write. Yep. Okay, so then my square, let's think about how we describe the area of the square. So area of the square is obviously just let's call the side length. I won't use x. X is already another variable, so let's call it, y and y. Okay. So we know that the total perimeter of this square has to be equal to 40 minus x. And if I call the side lengths of the square y, that means that the perimeter of the square is 4 lots of y, and that has to be equal to 40 minus x. And so that tells me that y has to be equal to 40 minus x over 4. Or you might choose to write that as 10 minus x on 4. That's fine. So the area of this square is going to be y squared, and we now know that that is y, because I'm trying to get both areas written in terms of x, so that then I can come up with an equation for the sum of the 2 areas that's in terms of x, which is to do with the wire, and then I can think about maximizing or minimizing. Okay, so this is 40 minus x on 4 all squared. Okay. So as I said, you might write this in lots of different ways. You might choose to say, well, that's 10 minus x on 4 all squared. You might then expand that out, perfect squares. 100 minus 2 times 10 times x on 4, so that's going to be 20 times x on 4, which is going to be 5x. And then plus x squared on 16. So however you choose to write it, that's fine. Okay. So what we want to do now is think about going back to what it is that we're trying to maximize or minimize. We're trying to maximize the sum of the areas. So I'm going to call that S. Okay. So let S equal the sum of the areas. sorry, sum of the areas. Okay, and so S is clearly going to be the area of the circle plus the area of the rectangle. We have got some like terms here, but they're not very pleasant. You can probably just leave them written separately. Okay, so we want to maximize that area, or minimize, sorry. What are we trying to do? Minimize. Now, I've probably written a bit big here. Let me just move that over. I'm going to run out of space. And so we want to think about where we want to hopefully find a minimum turning point on this particular graph. Now, it is a parabola. It's a happy parabola, so it should have a minimum turning point, but let's find it. So ds dx is going to be at 2x on 2 pi, so that's just going to be x on pi, plus 2x on 16, so that's going to be x on 8, minus 5. And we want that to be equal to 0 for the stationary points. Okay, so we might look at here, we've got a common factor of x, so we might write this as 1 on pi plus 1 on 8 times x, minus 5 equals 0. Sorry, I'm going to lose that equals there. You might look at simplifying that fraction to get a common denominator. We're going to need to do that at some point. So common denominator will be 8 pi, so this is going to be the same as 8 plus pi over 8 pi times x, take away 5 equals 0. So let's add 5 at the same time. And so therefore x is going to be 5 divided by 8 plus pi on 8 pi, which means it is 5 times 8 pi on 8 plus pi. And so that is 40 pi on 8 plus pi. Now obviously if we've got our CAS, the first thing I would have done once I had come up with my equation would be to define the sum in terms of x, define the sum in terms of x as being x squared on 2 pi. Sorry, I knew that was going to happen. Let's try all of that again. Delete that from there, that needs to go under there. X squared on 2 pi plus x squared on 16 minus 5x and plus 100, and then shift minus to differentiate, with respect to x, we're differentiating s of x, and then we are solving that derivative equal to 0 for x, and we are getting exactly what we found. Now I'm going to press Control Enter here just to get a sense of roughly how big that is. Let me just be clear about the accuracy that we're asked to give our answer to. Okay, so it doesn't specify, so we want to be exact. I'm going to keep things exact. But I need to think a bit about using a sign diagram to justify. Now, you could make a statement about the fact that this is a positive quadratic, the shape will be this, and so therefore we have a local minimum. Or you could use a sign diagram to justify it. But you do need to justify, because all you've done at this point is shown that that is the x value that gives a stationary point. You now need to show that this is actually a minimum stationary point. Okay, so I'm going to construct my sign diagram here. So when x equals something, what does ds dx equal, and what does that mean for the shape of the graph? Okay, so we didn't do a sign diagram in the last one, so let's just practice that here. But it does necessitate that I get a sense of roughly how big that number is, which I guess we could have done in a couple of ways. If we approximate pi as being somewhere close to 3, it's about 120 on 11. So, you know, it's certainly going to be, you can get a rough sense of about how big it would be. Okay, so our x value is 40 pi over 8 plus pi. And we know that at that x value, ds dx is equal to 0, and so that's where we have a stationary point. We've worked out that 40 pi over 8 plus pi is about 11.3, and so perhaps if we look at, 10 and 12 either side, we work out what ds dx is equal to. So we're substituting the value of 10 into our rule for ds dx. Okay, so that's going to be, and again, we can look at the simplified version. So that's going to be, yeah, we can work that out. So I'm just going to use my CAS here to get these as decimals. As I said, possibly if you're working by hand here, actually the better justification is the fact that you have a positive quadratic, and therefore it will be a local minimum. So I'm just going to substitute. So what I've just done there, I'm just going to show that again. I've just scrolled up and got my derivative of s of x, and then I want to sub into it, so I need to do given that x is equal to 10. Control enter, so that's about negative 0.57, and when x equals 12, okay, 12, sorry, control enter, that's about 0.32. Okay, so negative and then positive. Just to be clear about the fact that if you want to substitute into a derivative, you can't just do, you have to do this given that x equals 10. You can't do s of 10 because that's not calculating s dash at 10, that's calculating s at 10, which will be a number, and then differentiating it, and the derivative of a number is always 0. So that's meaningless. You've got to do derivative of s of x and then substitute 10 into that, which is what the given that sign allows you to do. Okay. So therefore, we know that when x equals 40 pi on 8 plus pi, s is a minimum. It's really important that you're careful about how you say that. Sometimes people say when x equals 40 pi on 8 plus pi is a minimum. That's not the minimum, that's the x value that gives minimum s. Now let's be clear about what question we want. So find the lengths of the two pieces. Okay, so we know that x is the length of one piece. We've now found that value. We therefore want to also work out 40 minus x. Okay, so this means that the lengths of the two pieces of wire are 40 pi on 8 plus pi centimeters, and 40 minus that. I'm going to get my CAS to do that for me. 40 minus, so I got it up here somewhere, that. So to get rid of that x equals. So that is 320 on pi plus 8. And yes, you can do that algebra yourself at some point, but I'm happy enough with that. If the question obviously asked for you for those lengths to correct to 2 decimal places, then you'd be hitting control enter and getting approximate values. But unless the question instructs it, which it doesn't in this case, it just says find the areas, find the lengths, sorry, with no instruction to give a value to 2 decimal places or 1 decimal place or 3 decimal places or 10 decimal places, and so we don't give an approximate decimal value, we give a nice exact value that in this case involves pi. Okay, so the third example, a storage container with a volume of 96 cubic metres is built on a square base with vertical sides. Construction materials for the base cost $10 per square metre, and construction materials for the sides and top cost $6 per square metre. What dimensions of the container will minimise the cost? So minimising cost. Give your answer correct to 2 decimal places. Okay, so we can use our CAS. To be honest, in most of this chapter, but in these Max-Min problems, you know, the work is in the formulation of the problem. I'm happy for you to use your CAS in finding the required answers. We're not really in the applications of differentiation test. The focus is, the focus is less on you doing the differentiation by hand and more on the do you understand how and when you use differentiation and you know when it is useful. So let's use our CAS here. So obviously though the first thing is what are we trying to maximise or minimise? We're minimising cost. I've highlighted that. So we're going to need to come up with an equation for the cost. Okay, so let's get our information organised and straight and think about how we're going to be able to do that. So we have a storage container, we're given the volume, 96 cubic metres, it has a square base and vertical sides. Okay, so it's a sort of rectangular prism. Okay, so we've got a square base and vertical sides. Okay, so something like that. So square base, let's maybe call the side lengths of the base x and the height. We don't know. So we don't know any of the dimensions. We do know the volume though. So we know that the volume of this is 96 cubic metres. We are trying to come up with an equation for the cost, and we're told about the relative costs of the sides and the base. And also, does it refer to a top? Sides and the top. Okay, good. So the sides and the top are all going to be $6 per square metre, and the base is going to be $10 per square metre. Okay, so let's think about what we've got here. We know that the area of the base is x squared square metres, okay? And so that means that the cost of the base is going to be the square metres times by 10. $10 for the per square metre for the cost of the base. So the cost of base will be 10x squared dollars. Okay. Let's think about the areas of the sides and the top. Okay. Area of sides and top. We've got 4 sides, and each of them has dimensions x times h, plus we've got a top which is x squared. Okay, so we've got 4xh plus x squared. Okay, and so the cost of the sides, is going to be at $6 per square metre for the sides and top. So costs of sides and top, So it should be 6 times this total area. Okay. So what's that going to be? 24xh plus 6x squared. Okay, and yeah, that's in dollars. This was in square meters. Okay, so our total cost then is going to be 10x squared, the cost of the base, plus 6x squared plus 24xh for the costs of the sides and the top. So that is 16x squared plus 24xh. Okay, however, we've got 2 unknowns in our equation for cost x and h, and so we need to eliminate one of those, and that's why we've got the information about the volume. So we know that the volume of this prism is x squared h, and that equals 96, and so therefore we know that h is 96 on x squared, and we can put that in our equation for cost. Okay, so that's going to go in here. So our cost equation, 16x squared plus 24x times 96 on x squared. Okay, so that's going to be, I've written too big again, it's okay, I'll go off to the side. 16x squared plus, let me just do 24 times 96 with my CAS, that is 2304 over x. So that's my formula for cost. Okay, so that's the hard bit. You can't, your CAS doesn't help you in doing that, so it's fine for you to use the CAS for the nuts and bolts maths. You still need to do a lot of maths to actually formulate the problem. Okay, so now we're trying to minimise cost. So we want to think about the stationary points for this cost equation. Okay, so let's work out the derivative of the cost. So I'm going to define the function in my CAS to help me be able to work through it efficiently. 16x squared plus 2304 divided by x. Oh, sorry, I haven't made it equal to anything. C of x. Okay, great. So now let's work out our derivative. Obviously we can do that differentiation ourselves, it's not particularly hard, but if we do it with our CAS, it means we'll have that expression in the CAS to use it. Okay, so it's 32x minus 2304 on x squared, and we want that to be equal to 0, so we're going to solve. So it's really important in your working that it's clear that you are solving derivative equal to 0, that you're writing down the relevant equation, even if you're using your CAS to do it. So x is 2 times 3 to the power of 2/3, which is approximately equal to 4.16 metres. Okay, we want to work nice and precisely with the CAS, so we'll use that more exact value. Now, we need to be clear that this is actually a minimum turning point. All we know is that this is a stationary point of the graph. We want to know, is this the point that actually gives us minimum cost? So compared to the previous examples where we've actually ended up with quadratic functions, and so we actually know whether it has a minimum or a maximum turning point without really needing the sign diagram, this is a different kind of function, and we don't know what this looks like. It's a combination of a quadratic and a hyperbola, and what will that look like? We could get our CAS to draw it for us, but then in order to actually justify that this is a minimum on the page, you would need to draw the graph on the page to say, look, you can see from the graph that this is a minimum point, and therefore it's just as easy to generate the sign diagram. So x values, derivative, and shape. Okay, so we know that when x is 2 times 3 to the power of 2/3, which is about 4.16, the derivative is 0, and therefore we have a stationary point. So let's take an x value to the left of that and an x value to the right of that. So let's just go 4 and 5. So the other thing that we learn is that this is the only stationary point on this graph. We've only got one x value when we solve the derivative equal to 0. So that's also an important fact. So let's just justify what kind of stationary point it is. So now I want to substitute 4 into my derivative. So I'm going to take my derivative, given that x equals 4. Okay. And then the same thing given that x equals 5. Okay, so this is equal to negative 16, so we're going down, and this is equal to 1696 on 25, which is clearly positive. Okay, so therefore we know that x equals, or x approximately equal to 4.16 meters gives minimum cost. Now the other thing to be clear, we'll talk more about this in the next video, is because this whole graph only has one stationary point, we know from this to this, there's only one solution to the derivative equal to 0. And if we know that that stationary point is a minimum, we then know the graph never turns around again. So it never gets any lower than that, ever. That is the lowest point on the graph. Okay? Alright, so we know when x is 4.16 we get minimum cost. Let's be clear about what the question actually asks us to find. What dimensions of the container will give the minimum cost? Okay, so the dimensions of the container are x, so x, which we know, we've worked that out, 4.16, and h. Okay, so it actually doesn't ever ask us for minimum cost. So this is where it's clear. Be clear about what the question's asking you for. What dimensions give the minimum cost? Okay, so we want to know h. We know that h is 96 on x squared. Okay. So h is 96 on x squared. So in this case that will be 96 on 4.16 squared. So I'm going to be a bit more precise about that with my CAS. 96 divided by, I'm going to go up and get this number up here, divided by that squared. Now I've got that x that copied down with that, which is a bit annoying. So if you'd rather not, you could I'd just type out more than 2 decimal places, type out to 4 or 5 decimal places, and that would be enough accuracy. Okay, so h is approximately 5.55. Now we wanted answers correct to 2 decimal places. Okay, so therefore dimensions for minimum cost are, that's a cuboid or a rectangular prism, it's got 3 dimensions, so they are 4.16 meters by 4.16 meters by 5.55 meters. Build a box with those dimensions, it'll have a volume of 96 cubic meters, and it will minimize the cost given the information that we've got in this particular question. Okay, the work today is from a worksheet, but I've actually changed the worksheet, so you can ignore this list of questions. I just want you to do the worksheet that I've set. It's a different set of questions, so you don't need to look at that particular list of numbers. Just do the questions on the sheet that I've set.